Hello student, good morning. I am Dr.A.K Sinha, Professor of Chemistry. Today I am going to discuss the actinide series. The actinoids include the 14 elements from thorium to lawrencium. First, I will tell the name of members. First member is atomic number 89, actinium. Its symbol is AC. And next is thorium, atomic number 90, symbol is TH. And third element is protactinium, PA, atomic number is 91. Next is uranium, 92, its symbol is U. And next is neptunium, 93, and symbol is NP. 94 is plutonium, Pu. 95 is americium, AM, americium, not Americum, americium. It is from America only, americium, AM. 96 is curium, CM. 97 is berkelium, BK. 98 is californium, CF. 99 is einsteinium, ES. 100 is fermium, FM. 101 is mendelevium, MD. 102 is nobelium, NO. And 103 lawrencium, LR. Then here you have seen all names are either on the name of scientist or place. Name has been given on the name of scientist or on the place, maybe country also. Now their electronic configuration I want to tell you, and radius. Electronic configuration and radius. But these things I will come to the electronic configuration, but little more I want to tell about the actinoids, also called actinium series. The actinoids are radioactive element. First important point. The actinoids are radioactive elements, and the earlier members have relatively long half-lives. Half-lives are more in the beginning, and after that middle, you can tell middle onward, the later ones have half-life values ranging from a day to 3 minutes, very less. In the beginning, the actinoids are radioactive elements, I told you, and the earlier members have relatively long half-lives. The later ones have half-life value ranging from a day to 3 minutes, very less, a day to 3 minutes. For lawrencium, Z is equal to 103. See, so less. The latter members could be prepared only in nanogram quantities. Their production is very less manufacture or production, you can tell, is less in nanogram quantities only. These facts render their study more difficult, because for the study samples are required, but here it is produced in very less quantity. It is prepared only in nanogram quantities. Then it actually restricts the study. These facts render their study more difficult because productions are very less. Now come to the electronic configuration. All the actinides are believed to have the electronic configuration of 7s square. Last orbit is 7s square. All the actinides are believed to have the electronic configuration of 7s square, and variable occupancy of the 5F and 6D subcell. Okay, and in the last 7s square is there, and variable occupancy of the 5F and 6D subcell. They have variable occupancy. The 14 electrons are formally added to 5F, though not in thorium. Z is equal to 90, that you have to not add. Okay. But from protactinium onwards, the 5F orbitals are complete at element 103. Okay. 14 electrons are formally added to 5F, though not in thorium. Thorium is an exception. But from protactinium onwards, the 5 orbitals are complete at element 103. The irregularity in the electronic configuration of the actinides, like those in lanthanides, are related to stabilities of the F0, F7 and F14 occupancies of the 5F orbitals. Irregularity, I am talking about the irregularities. The irregularities in the electronic configuration of the actinoids, like those in lanthanides. In lanthanides also it happens. In both cases are related to stabilities of the F0, F7 and F14 occupancies of 5F orbitals. You know that F0, F7 and F14, that they are stable because it is a empty. First is empty, F0. F7 means half filled, it is also stable, and F14 is fully filled. That's why it shows irregularity, means these three states are stable states. That's why it shows irregularities like lanthanides. Here also these states are stable states. Thus the configuration of americium and curium are Rn, means radon electronic configuration, and after that 5F7 6s square, and next curium 5F7 6D1 7s square, 7s2 you can tell. After the radon configuration 5F7 6D1 and 7s2. Okay. This is the curium electronic configuration, and americium configuration, that is after the radon 5f7 7s2. Although the 5f orbitals resembles the 4f orbitals of their angular part of the wave function, they are not as buried as 4f orbitals. 4f orbitals are more buried. Okay, and hence 5f electrons can participate in bonding to a far extent, because 4f orbitals are not as buried. Here, it's understand this important point. Although the 5f orbitals resemble the 4f orbitals, 5f and 4f resembles. Okay, 5f orbitals resemble the 4f orbitals in their angular part of the wave function. They are not as buried as 4f. 4f is more buried. Okay, hence 4f electron will not take part in the bonding, but 5f are not buried. Means 4f is more buried than 5f. Hence 5f electrons can participate in bonding to a far extent, not the 4f. 4f is buried, more buried, means that electron will be nucleus will attract the 4f electrons more tightly than 5f. Now I am coming to the point ionic size of actinoid series. The general trend in lanthanide is observed. The general trend in lanthanide is observed in the actinoids as well. Just in the term of size, trend I am talking about. The general trend in lanthanide is observable in the actinoids as well. There is a good gradual decrease in the size of atoms, or M3 plus. M means, capital M means metal, M3 plus. Okay, cation 3 plus. There is a gradual decrease in the size of atoms, or 3M plus ions across the series, means slowly in series it is decreases. This may be referred to as the actinium contraction, just like lanthanide contraction is there, here also actinoid contraction, same basis. Okay, then this decrease in ionic size is due to the actinoid contraction, like lanthanide contraction. The contraction is, however, greater from element to element in this series, resulting from poor shielding by FF. This I was discussing. There is a general range of this ionic size. I was discussing general trend of lanthanides is observed in actinides also, and there is a gradual decrease in the size of atoms, or 3 plus ions across the series. This may be referred to as the actinoid contraction, or you can tell it is similar, this contraction, actinide contraction. Here also in actinide series, it is this decrease in ionic size is due to actinide contraction like lanthanide contraction. The contraction is, however, greater from element to element in this series, resulting from poor shielding of 5f electrons. In 5f electrons, their shielding is poor, means they are not shielding properly. In 4f, it was shielding was proper, good, hence nucleus effect was in here. In actinide series, nucleus effect is less because it is not proper shielded. Electrons are not shielding properly to each other. But in 4f electrons, their electrons are shielding to each other properly. Okay, that's why this 4f nucleus has more effect on 4f, okay, than 5f. That's why 5f electrons can take part in bond formation. Then just I will tell about the values. What are the actually value of radius? What has been observed, that I want to tell you now. That is actually I will tell for the M3 plus. M3 plus, what are there? These things, radii in picometer. Actinium means 39. Its symbol is AC, and electronic configuration, that is the 6d1 last in the last I am telling you 6d1 7s square. After this configuration, that is the ideal gas configuration, not ideal gas, in inert elements you can tell better. Okay, they are also gas, only inert gas or ideal gas you can tell. Then last, that inert gas, after the inert gas configuration, I am telling you in the last electrons are 6d1 7s square. Okay, means after the inert gas configuration. And 5f is 0, incomplete, not at a started, 5f 0. And this because in outermost 3 electrons are there, 6d1 7s2, hence maximum they can release 3 electron can be removed, hence it can give M3 plus. Correct? M3 plus. 3 plus means 3 electron can be removed or is removed. Then 1 plus 2, 3 electron gone. That's why metal became from M, now it became M3 plus. It lost 3 electron, and its size is 111, 111, 111. Correct? This is size of M3 plus, 111 picometer. Now thorium 90 Th. Thorium means Th. Its electronic configuration, now one more electron, every time one electron will go to the F. Then now 5f0 became 5f1. Then now before these things 6d square, or means 6d2 and 7s2. This is also, you can tell here you have just I told 6 in the case of actinium AC, electronic configuration was this thing 6d1 7s square. Okay, 6d1 7s square. Now one electron came, increased, then now it became two possibilities are there. Then 6d2 7s2. Then total 4 electrons are there, and that can be removed. Then m plus 4, m can see now it can lost 4 electron because 4 electron is there, 6d2 7s2. Then two possibilities are there. They can lose 3 also, they can lose 4 also. Okay, when they will lose 3 electron, then 1 electron will be remaining. In that situation, that 1 electron will occupy 5f1. Now it was 5f0 in case of actinium, but now 1 increased. Then there is two possibilities. It can go, 1 electron can go to the D and 1 electron can go to the F. Hence, removal of 3 electron is also possible. 1 plus 2, D1 and 7s2. Then plus 3 it will give, M3 plus it will give. And if you can say this 5f1, if 3 it will give, then 1 electron will be remaining. Then that time when 3 electron it will lose, 4th electron will go to the 5f1, and then it will form these things m3 plus, but 4 is also possible. If all 4 electron is lost, if it will this all 4 electrons, if it will lose, then it can form M4 plus also. But what is the size, its radius is not known. Okay, but M4 plus its value is given 99. Okay, M4 plus that radius is in picometer is given. Okay, and in this case, after losing this 5 to 7 square, because it will get 5f0 after losing 4 electrons, no electron will left out in the f0. That's why it is stable. In M4 plus state, it is stable, and its size is radius is 99 picometer. Now next 91, that is the protactinium. Then Pa, protactinium is called Pa, and now one more electron will come. Then where it will go? Then it will go to the F, and then now it became 5f2 6d1 7s2. Then now here, that what are the possibilities to lose? How many electrons? Then it can lose 4 it can lose. Okay, then total 5s are there, but 4 it will lose. Then this who are that electron? Then 7s2, that 2 electron, 1 d1, that they will lose, and 1 from F it will lose, and 1 will be remaining. Okay, then it will form M3 plus. If they are losing 3, then it will form 3 plus. If they will lose 4, it will form 4 plus. Then here also that these things M3 M3 plus value is not, actually this stable 4 is the stable state in this case, 4 plus. That's why direct value is 96. Now see, it began to decrease. It was 99 in the case of thorium, 90, and in protactinium Pa 91. Now it decreased. It became 96. From 99 it decreased 96. 3 picometer decreased, and 3 plus is not favorable. Now uranium 92, one more electron came. It will go to the 5f only. Okay. Because why they are going to the 5f despite 6d is available? Then this is due to energy, less energy. 5f have less energy than 6d. Okay, very close, but 5 is lesser than 6d. That's why first it will go to the 5f and then 6d will start filling. Okay, because both have less difference, but 5 is more, just lesser than 6d. 6d is little more. That's why when both will be almost equal, only that time it may go to the from 5f, from the 5f it can go to the 6d. Okay, only in rare you have seen in the case of only 90 you have seen that it went to the 5, d2 was there, it went to the 5f1. If they are almost equal, then only it is possible, but in almost all cases 5s is less than, energy is less than 6d. Then now uranium, one electron went to the f, now it become 5f3 and 6d1, 7s square. Then now 5f3, 6d1, 7s2. Then 3 electron, certainly it will go. In that situation 5f3 will remain. 5f3 will remain. Then 6d1 and 7s2, both electron just it lost. Then it can lose. Then state 3 is possible, plus 3. Then it's actually this ready is 103 picometer, M3 plus, and in case of M4 plus, now further decreased 93. It forms both. Here 4 is also, plus 3 is also, 3 plus is also possible, 4 plus is also possible. Then 3 plus is 103. In the first case it was 111. Now after that here now it is 103. In 3 plus also size decreased because radii decreased, and M4 plus also decreased from this. Now it is 93. From the 99 now it became 93. It is decreasing. Uranium 92. Remember uranium atomic number. All actually this is asked. Okay, actinium, thorium, protactinium, uranium, neptunium, all you should remember. Then now come to the uranium 92. Now one more electron came. Uranium already told you. Now neptunium 93. Np, symbol is Np. Then neptunium, now one electron came, then now F became 5f4, 6d1, 7s2. Then now again 3 electron easily can be removed. Then 5f4 will remain. Then here now again for M3 plus radii decrease. Now it became 101. Here M 4 plus is also possible. M4 plus is also possible. In that situation 5F3 will remain. Okay, because it was 5F4. Now 5F3 will remain. One electron from F also gone. Then it formed M4 plus. And now ionic grade is again decreased. Contraction is going on. Now it became 92. Now plutonium 94. Plutonium Pu. Now F5F became 6. 4 was there. Then now 6D1, because now 5F become 6D1 is not there. Directly actually one electron came, then it should be 5F5. And this one electron of D also came here in F. Now it became 5F6. 5F6. Why it is happening like that? Because 5F6. Now they are closer to half filled. Anytime it can take one electron from the 7s2 are there. It can take. Then it become half filled, very close. And due to that reason, now they can taken from D1 electron was there, it has taken. Then now it became 6. Then here 3 electron they can lose. Then 5F5 will remain. Okay. And in that case, total is actually 8. 5F6, F6 and S2, total 8. Then 3 will go, then 5 will remain. 5F5 will remain. Then here again, both possibilities are there. 3 plus, M3 plus, M4 plus. Then when it is a 3 plus situation, M3 plus, then now again decreased. Radius decreased. Now it became 100. And if 4 plus, then again it decreased. Now from 92 it became 90. Then now come to the 95, americium. Americium, don't tell, americium. CIUM. You are telling always na actinium. Actinium, thorium, actinium, protactinium, uranium, neptunium, plutonium, IUM. Here also you can tell americium, IUM. Actually it is coming from the America word only, but IUM you have added. Okay, americium, AM. Then now one more electron came, then 5F6 became 5F7, 7s2. Now D gone, D electron also it is taken. Then now it is completely half filled, 5F7, 7s2. Then here again both possibilities are there. It can lose 3 electron and 4 electron also. Then total electron is 9. 7 plus S2. 9. Then if out of 9, if 3 will go, then 6 will remain. 5F6 will remain. And if 4 will go, then 4 will remain. 5F out of 9. In 9, 3 will go, then 6 will remain. Okay. And if 4 will go, then 5 will remain. Then if M3 plus, if they are losing 3 electron out of 9, then 6 will remain, 5F6 will remain. Now this became 99. Ready became 99, again decreased. And in this case also 4 plus, M4 plus, it also decreased. From 90 it became 89. Okay, then in both cases, in M3 plus and in M4 plus, radii value is decreasing. Now next is curium, CM, Chief Minister. CM, okay, just for remembering point of view. This curium, CM, 5. Then here one more electron will come. Then this time, because now already F is half filled, it does not want to, I can say, destabilize. Okay, it does not want to be unstable. Then now that electron will go to the 6D. 6D1 start. It was closed, now start, because they want to maintain 5F7. Then now new electron will go to the 6D1. Then again both possibilities are there. Losing for 3 electron, 6D1, 7s square, 7s2. That 2 electron, 3 electron, 1 plus 2. Then now total electron is 10. Then out of 10, if 3 will go, then 5F7 will remain. Okay, 5F7 will remain, and it will form M3 plus. Now its radii is almost same, means same only 99. Only when 4 electron it will lose, means M4 plus. That situation, this will decrease, radius will decrease. In 4 plus condition, it became 88. Okay, in 3 plus condition, values are same, 99. Now curium, I told you, CM, berkelium, BK, berkelium 97, curium was 96, now it is 97, berkelium. Then berkelium, now 1 electron came, new electron, then 5F7, 6D1 was there. Then now all electron D will be removed. That electron will be taken by F. Then it will become 8, and now new electron 9. Then now it became 5F9, 7s2. Then now total 11. 5F9, 7s2, 11 electrons are there. Then now in this situation, here what will happen? If 3 electron will go, then 8 will remain. Then 5F8 will remain. Okay, and in that situation, 3 plus, M3 plus will become 98, decreased, radius decreased, and here M4 will be more stable because 5F7 is remaining. 5F7 will remain after losing 4, hence it is stabler. Then now radius decreased always continuously for both M3 plus and M4 plus. Radius is decreasing. Now it became 87. Now 98, californium, from the californium, CF. Then now one more electron came. Then now 5F10. 9 was there. Now it became 10. 5F10, 7s2. Then now out of total is 12. 10 plus 2, 12. Then now if 3 will go, then 9 will remain. If 3 will go, 9 will remain. Then 5F9 is remaining, and 3 plus, now its size again same like 98, both are 98, and M4 plus means if they will lose 4 electron, then out of 12, 8 will remain, 5F8, and radius became for 4 plus 86, again decreased. Then this I have told you about the how it is decreasing. Further also Einsteinium in the name of Einstein, 99. 99 is Einsteinium. And 100 is Fermium, FM, in the name of scientist. Mendelevium, MD, in the name of scientist. Okay, Nobelium, the name of scientist. Lawrencium, also name of scientist. Then this 98, up to 98 value is observed, but Einsteinium onward, 99 Einsteinium, Fermium 100, 101 is Mendelevium, 102 Nobelium, 103 Lawrencium. For all these elements, values are not observed, not found. Okay. Then this I have told about the electronic configuration and contraction of actinium series, that is called actinoid contraction. Question is asked. Oxidation state also actually it is separately it is discussed, but all values I have told you that M3 plus and M4 plus means 3 plus oxidation state and 4 plus oxidation state is common here. There is a greater here in actinoid series, there is a greater range of oxidation states, which in part attributed to the fact that 5F, 6D and 7S levels are of comparable energies. Their energies are very close, that is called comparable. That's why because 5F, 6D, 7S, these energy level, these levels have almost I can say same, not 100% same, comparable. That's why various range of oxidation state is seen in this series. Okay. The known oxidation state of actinoids already I have discussed. The actinoids show in general +3 oxidation state. +3 oxidation state generally it will show. The elements in the first half of the series frequently exhibit higher oxidation states. Okay. For example, the maximum oxidation states increases from +4 in thorium, but it will go to the +7. Then it oxidation state increases from +4 in thorium to +5, +6 and +7 respectively in protactinium, uranium and neptunium. Okay, because possibly that time you have seen possibility was there for higher also, because they will maintain these things 7 +7 half filled or F0 they will maintain, and also they can maintain F14. Then for this region they can show higher oxidation state. Okay. Then in the beginning +3 I told you, but after you can say 50% first half, second half means it can show higher oxidation state, +5, +6, +7 respectively in Pa means protactinium, U uranium, Np thorium. Okay. But decreases in succeeding elements. After that it will be decrease, means it will show only +3 oxidation state. The actinoids resemble the lanthanides in having more compounds in +3 state than in +4 state. However, +3 and +4 ions tend to hydrolyze. Hydrolysis will take place for +3 and +4 ions. Because the distribution of oxidation states among the actinides is so uneven and so different for the former and later elements, it is unsatisfactory to review the chemistry in terms of oxidation states. Okay, then already I have told you this thing, oxidation state, but now again this I want to tell the elements which are showing more oxidation states, more number of oxidation state. Then protactinium protactinium, it shows 3 oxidation state, +3, +4, +5. And uranium, it shows again one more, +3, +4, +5, +6. And neptunium again one more, highest, means +3, +4, +5, +6, +7. Plutonium again same condition, +3, +4, +5, +6, +7. These two are these two, neptunium and plutonium, show highest oxidation states. And americium again it will show up to 6, just like uranium. Americium also show same, +6. And curium onward it is less only, curium only +3 and +4, berkelium only +3 and +4, californium, einsteinium, fermium, molybdenum, niobium, lawrencium, all are showing +3 oxidation state. Now I am coming for these things, general characteristics. Now I will discuss general characteristics and comparison with lanthanoids. The actinides metal are all silvery in appearance, but display a variety of structures. The actinide metals are all silvery in appearance. It will look like a silver in color, but display a variety of structure. The structural variability is obtained due to irregularities in metallic radii, which are far greater than in lanthanoids. Okay, these radii I am telling about. There is irregularities in metallic radii which are far greater than in lanthanoids. Here you can say more these differences are there. The actinides are highly reactive metals. You remember, the actinides are highly reactive metals, especially when finely divided, when it is in powdered form. In that situation, that is called finely divided, then that time it is highly reactive. And particularly, means in general way it is highly reactive, especially when finely divided, means in powdered form. The action of boiling water on them, what will happen if boiling water will come in contact with the actinides? The action of boiling water on them, for example, gives a mixture of oxide and hydride. It will give oxide and hydride. Okay, and combination with most non-metals. Combination with most non-metals takes place at moderate temperature. And it can react with non-metals also, like halides. Hydrochloric acid attacks all metals. HCl, hydrochloric acid attracts all metals, but most are slightly affected by nitric acid owing to the formation of protective oxide layers. Why nitric acids have less effect? Slightly affected by nitric acid. What is the reason? Question is asked. Then due to the formation of protective oxide layers, nitric acid, if you will actinoids plus nitric acid, okay, then first it will form oxides on the metal NO. Generally oxide, many layers of oxides will be formed on actinoids. Okay, that's why it is less affected, because if a layer is formed, then further nitric acid will have less effect on actinoids. Alkalis have no action. It will not react. Actinoids will not react with alkalis. Then here you have seen with acid reaction is there. When it reacts with acid, it means they have basic nature. If acid is reacting, actinoids are reacting with acids, means they have basic nature. That's why they are reacting with acid. And why they are not reacting with alkalis? Due to same reason, because that is a basic. How they will react with alkalis? Both have same nature. Actually, base with dissolved in water is called alkalis. That is a difference between alkalis and bases. That's why all bases are not alkalis, but all alkalis are bases. That's why they are not these actinoids are not don't react with alkalis. Means alkalis have no action on actinoids. The magnetic properties. Come to the magnetic properties. Magnetic properties of the actinoids are more complex than those of lanthanoids. Although the variation in the magnetic susceptibility of the actinoids with the number of unpaired 5f electron is roughly parallel to the corresponding results for the lanthanoids. The latter have higher values. Here number of unpaired electrons, so that unpaired electron is responsible for magnetic properties, that is a common. Then here actinoids with the number susceptibility I am talking about, magnetic susceptibility of the actinoids with the number of variation in the magnetic susceptibility of the actinoids with number of unpaired 5f electron is roughly parallel to the corresponding results for the lanthanoids. Same way. Okay. But lanthanoids, the latter means lanthanoids have higher values. It is evident from the behavior of the actinoids that the ionization enthalpies of the early members of the actinoids, though not accurately known, but are lower than for the early lanthanoids. If you will compare behavior of the actinoids, particularly for ionization enthalpies, ionization energy of the early actinoids, early members of the actinoids, though not accurately known, but are lower. Actinoids have lower ionization energy than for early lanthanoids. What is the reason? The reason is very clear. They are actinoids that electrons are not shielding properly. They have less effect of these things. this thing's less effect of nucleus. That's why it can be removed easily. It can be removed, means ionization energy will be less, ionization enthalpy will be less. Okay, that actinides enthalpies, ionization enthalpies, it is observed, it has been observed that the behavior of the actinides, that the ionization enthalpies of the early actinides, though not accurately known, but are lower than for early lanthanides. Why? Because it easily can be removed. That's why it is less than lanthanide. Lanthanide is properly shielded, hence this nucleus has less this things effect. They are properly this electrons in lanthanides. From that it is very easy to very difficult to remove the this thing, remove the electron from the 4f. Okay, this is quite reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, they will penetrate less into the inner core of electrons. Okay, why it is happening? Lanthanide, this ionization energy for actinides are less than lanthanoid. Why? This is I can say reasonable, since it is to be expected that when 5f orbitals are beginning to be occupied, okay, they will penetrate less into the inner core of electrons. They will be only in the beginning. As it will go closer to the nucleus, only then will be tightly held. Okay, the 5f electrons will therefore be more effectively shielded from the nuclear charge than the 4f electrons. 4f electrons are not properly shielded. 5f electrons be more effectively shielded from the nucleus charge than the 4f electrons. Okay, that's why its energy is required, because nucleus has less effect on 5f electrons. That's why easily it can be removed in comparison to the 4f electrons. They are closer and properly shielded. Because the outer electrons are less firmly held, they are available for bonding in the actinoids. That's why 5f are easily available. That's why it will take they will take part in the bonding. A comparison of the actinoids with lanthanoids with respect to different characteristics, as I have discussed, reveals that behavior similar to that of lanthanide is not evident until the second half of the actinide series. Means after that only it will be different. Before that it will be similar. Okay. However, even the early actinides resemble the lanthanides in showing close similarities with each other. Second half will not show similarities. First half it shows similarities with each other and in gradual variation in properties, and which do not entail change in oxidation state. If both have same oxidation state, then properties will be similar. The lanthanide and actinide contraction have extended effects on the size, and therefore the properties of the elements succeeding them in their respective periods. This is important things. Again I am telling you, the lanthanides and actinide contraction have extended effect on the size. They have effect on size, same type of effect, and therefore the properties of the elements succeeding them in their respective periods. It affects the succeeding members, elements. It affects the properties of the elements succeeding them in their respective periods. The lanthanide contraction is more important because the chemistry of elements succeeding the actinides are much less known at the present time. The lanthanide contraction is more important. Why? Because the chemistry of elements succeeding the actinides are much less known at present time. Now one question is there, important question. I will tell you, just you should remember also. Name a member of the lanthanide series which is well known to exhibit +4 oxidation state. Lanthanoid, not actinides. Lanthanoid who have +4 oxidation state. You know they have +3, but one has +4 oxidation state. Who is this? Tell the name of the lanthanides. Member of the lanthanides is, what is the name? Then it is a cerium, atomic number 58. It has +4 oxidation state. Okay. Now I am telling about some applications. Application of D and F block elements. Okay. Because when you are studying anything, then why you are studying? Without use and application, you can't study. If anything has no application, no use, then why will you study? Not required. All things have importance due to their application, use. It applies to everybody, not only of these elements, even for all things. If anything has no value, then nobody will know that things. Even for any person, if they are not knowing anything, who will ask that person? They will be just like an old man. They will be sitting in one place. Correct? They have also good role, guidelines. They can guide so many things, but just bodily I am talking physically. They are not very active in that sense. Then here I am telling you use, applications. Always use are studied and the end. Then here just to understand where it is used. Iron and steel, Fe, that is coming under the lanthanide series, first series. Iron and steels are the most important construction material. See the importance of Fe. Iron and steels are the most important construction material. You know well. Their production is based on the reduction of iron oxide. You know that Fe2 plus, it can give Fe3 plus. Fe3 plus can it may come back to the Fe2 plus, or ordinary Fe will convert to Fe2 plus, and Fe2 plus will come to Fe, pure metal. Fe2 plus, after the reduction it will convert to Fe metal. Okay, then this is the very, very important properties. Means I am talking about the production. Their production is based on the reduction of iron oxides, the removal of impurities, and the addition of carbon and alloying metals such as chromium, manganese and nickel. Again I am telling you, iron and steels are the most important construction material. Their production is based on the reduction of iron oxide, the removal of impurities, and the addition of carbon and alloying metals. Alloying metals means such chromium, manganese and nickel. Generally it is mixed with iron and their property will change. Different type of steel, they will form different type of steel or stainless steel. Some compounds are manufactured for special purposes such as titanium oxide for the pigment industry. Titanium is also used, titanium and carbon is also used in artificial, you can say heart, or you know that in heart valve is there. Then if suppose it is not working, then it can be replaced with other valve in heart. Then there titanium and carbon both are used. Both metals are used, titanium and carbon both are used in artificial valve of the heart. And pigment, as a pigment also titanium oxide is used for the pigment industry. And manganese, here we are studying this for D and F block elements application. Then titanium oxide is used, TiO, for the pigment industry means colored, and MnO2 for use in dry battery cells. You might have seen, if any used battery if you will open, then you will see in torch you are using dry cell. In that dry cell, if you will just open it, and then you will see black color material will be there. That is actually MnO2, manganese dioxide, for use in dry battery cells. Next application, the battery industry also requires Zn and nickel cadmium. Nickel and cadmium, all three are Zn, nickel, cadmium, all are required. Okay, in battery only these are used. The element of group L11 are still worthy of being called coinage metals. The elements of group 11, just like copper you have seen, copper, silver, gold. Then the elements of group 11 are still worthy being called as a coinage metals. And this I told about the coinage metals. Although silver and Au means or gold are restricted to collection items, this although silver and auric are restricted to collection items, and the contemporary UK copper coins, in UK copper coins will be there. Actually just like a silver coin, gold coin, it is there like that way. Copper coin is also there in UK. It is in contemporary in UK. Copper coins are copper coated steel. Now copper coins means that will be a steel, but copper coated, that is called copper coated steel. The silver UK coins are copper nickel. It is made from the copper and nickel, but it is called silver UK coins. Silver UK coins are made from copper nickel. Many of the metals and their compounds are essential catalysts in the chemical industry, that you know. If you will see any catalyst, they will come mainly from D and F block elements. V2O5, vanadium pentoxide, catalyzes the oxidation of SO2 in the manufacture of sulfuric acid. Already I discussed vanadium pentoxide, and vanadium is coming under this D and D block elements, but all are transition elements. Whatever I am discussing for transition elements. Then V2O5 catalyzes the oxidation of SO2 in the manufacture of sulfuric acid. Titanium tetrachloride, it will react with aluminum trimethyl or trimethyl aluminum, you can tell, forms the basis for Ziegler catalysis used to the manufacture of polythene. Polyethylene, also called polythene. Then titanium chloride is used with titanium chloride, TiCl4. It is used with trimethyl aluminum. Trimethyl aluminum, both are used together. TiCl4 with AlCH3, AlCH3 whole 3, trimethyl aluminum forms the basis of Ziegler catalyst used to manufacture polythene. Iron catalysts are used in the Haber process for the production of ammonia from nitrogen and hydrogen mixture. Already I have discussed. Nickel catalyst enables the hydrogenation of fats. If fat is there, then their hydrogenation can be done from unsaturated to bring saturated. Unsaturated is not good. Okay, it will be oil, OILS, oils, unsaturated. And sometimes you want to convert unsaturated to fat, then it will become saturated. Then saturated, there will be no reaction. Okay, unsaturated means double bond, triple bond. That you want to just double to convert triple or double bond to single bond. Single bond means saturated. Then nowadays all oils are coming saturated oils. Okay, then it is from the unsaturated fat, it is converted to saturated. Unsaturated is more reactive because of a double bond or triple bond. That was to stop the reaction. Now it is converted to saturated, means hydrogenation they will do, then double bond will convert to single bond. Triple also, if it is there, will be converted into a single bond. Then that time it will be called saturated. Then this fat, oil and fat will be converted to oil. Then this I have told you that nickel catalyst enables the hydrogenation of fats to proceed. In the other this I am talking about other use in the Wacker process, WACKER. In the Wacker process, the oxidation of ethine, YNE, triple bond, ethine, oxidation of ethine to ethanol, aldehyde, AL, ethine to ethanol is catalyzed by PdCl2, palladium chloride. Palladium chloride is also a catalyst, PdCl2, palladium chloride. Nickel complex are, again you come to the nickel. Nickel complex are useful in the polymerization of alkynes and other organic compounds such as benzene. Now another very most important application I am telling you, the photographic industry relies on the special light sensitive properties of silver bromide. Photochromic glass you might have seen. Photochromic glass means if you go to the sun, then it will change the color. Glass will change the color. When you come to the dark, that time again color will change. Then this is due to the presence of silver halide, particularly silver bromide. But if you are observing, suppose that after going to the light with photochromic glass, Then if it is a brown, reddish brown, then it means due to the presence of bromine, silver bromide. This bromide, its color is, bromine color is reddish. Correct? Then this silver bromide, actually, if you go to the light, what will happen? Silver bromide will vaporize. As soon as the light will come in contact with the silver bromide present in the glass, then it will vaporize. And when it will vaporize, then light effect will be less. Your eye will not feel that in front light is there. Intense light of the sun will be reduced. But when you will come to the shade or the room anywhere where sunlight is not there, then again it will condense. It will condense, and again you will feel normal. Means in the sunlight, in the presence of sunlight, it will vaporize, and in the absence of sunlight, it will condense. Correct? Then it is a very, very important application of silver bromide. Okay, it is a light sensitive properties. It has silver bromide has light sensitive properties. So now I have finished actinoids. Complete D and F block elements I have finished. Next class I will start new chapter. Okay, thank you.